At 3:34 a.m. on the 27th of February 2010, Chile was struck by one of the most powerful earthquakes ever recorded, a magnitude of 8.8 on the Richter scale, producing ground accelerations up to 0.74 G. Despite modern seismic design codes, both buildings and slope failed catastrophically. Chile lies along the Pacific Ring of Fire, one of the most tectonically active zones on Earth. Here, the dense Nazca Plate subducts beneath the South American Plate. As stress accumulates at this convergent boundary, it's suddenly released as seismic waves that propagate through the crust. These waves cause intense shaking, transferring dynamic loads into both structures and the ground beneath them. A building subjected to earthquake loading behaves like a spring mass damper system. As the ground shakes, the foundation moves laterally, but the building's mass tends to remain in place due to inertia. This resistance to motion generates a horizontal inertial force. Additionally, the building's stiffness measures how much force is required to produce a given horizontal displacement, while the natural period describes how quickly the structure oscillates. When the ground and the structure share similar natural periods, resonance occurs, dramatically amplifying movement and internal forces. To explore this, we built a 3-story spaghetti structure with an egg representing the building's mass to observe how it would respond under shaking. In our test, the structure collapsed due to failure in the joints of the foundation, whereas symmetrical models distributed loads more evenly and remained stable. This small-scale experiment reflected what occurred in the Alto Rio building during the 2010 Concepcion earthquake, where a flaw in reinforcement caused a soft-story failure, reminding us that even minor design imbalances can lead to disaster. During the 2010 earthquake, the Las Palmas tailings dam underwent cyclic loading, which raised pore pressures within saturated sand, causing complete loss of shear strength. This caused liquefaction within the dam, causing the soil to flow more than 500 meters downstream. We reflected on this as civil engineers by first considering the fundamentals of slope stability. A soil slope remains stable when the driving forces, caused by gravity acting downslope, are less than the resisting forces, which come from the friction between soil particles. The angle of repose, around 30 to 40 degrees for dry sand, represents the steepest angle at which a slope can stand without sliding under its own weight. Stability is often expressed using the factor of safety, defined as the ratio between resisting and driving forces. When the factor of safety is greater than 1, the slope is stable, but when it falls below 1, the failure occurs due to increased instability. The results showed a clear negative correlation between peak horizontal acceleration and the final stable angle of the slope. This observation supports pseudostatic theory, as the factor of safety decreases as the horizontal acceleration increases. As civil engineers, our role is not to eliminate risk, but to understand, predict, and manage it through design. The Chile earthquake reminds us that safety isn't achieved by resisting nature, but by working with it, by designing systems that move, absorb, and adapt.